Hello everyone. We already have started discussion related to sensor systems and we have seen a few circuits already. For example, we started with basic circuits, that is voltage divider circuit, and how this circuit is useful for sensor integration, and then we have started amplifiers. In case of basic circuit discussion, we also have seen another circuit which is Wheatstone bridge, and we also have seen how we can use this Wheatstone bridge circuit for sensor integration. And then we have seen different types of amplifiers, how we can design amplifiers that can sum input voltages. Then we have seen an inverting amplifier, a non-inverting amplifier, and finally we discussed what is a differential amplifier. In all the cases, the purpose of the amplifier is to amplify the signal. In case of summing amplifier, we said that sometimes we need to add different voltages. For example, there are different sensors and you need to add the voltage of all these three sensors for certain operation. You can use a summing amplifier, and a summing amplifier provides you an option that you can specifically amplify a single voltage out of say many, and then you can add that voltage with others. You can amplify all the voltages in the input side, and you can make a circuit of your choice that will serve the purpose. Okay. And in the last lecture, we finished the differential amplifier discussion, and we have said there is one more amplifier which is very important, and this amplifier is known as instrumentation amplifier. So to begin with, I'll show you the schematic of an instrumentation amplifier IC, which is AD8422. This is a basic instrumentation amplifier. It has 4 different pins as it is shown over here, and once you have the IC, you will find there is a dot in one side of that IC, and that indicates from where you should start counting the pins, because you should know what is terminal 1, what is terminal 2, what is terminal 3, and then you should know which one is terminal 1, because usually the ICs are black in color and you will find there are terminals in both the sides. Now this terminal can be 1, this terminal also can be 1, this terminal also can be 1. So there are 4 different possibilities which we may consider as first terminal. Just to avoid that confusion, in the IC itself you will find a small dot that is kept, and that dot indicates which terminal is terminal 1, and then you can calculate the number of terminals the way it is shown. The next one is 2, then 3, then 4, then the opposite to the 4th terminal is your 5th terminal, then 6th, 7th and 8th. So this is a basic instrumentation amplifier. The number is AD8422 and it has 4 different terminals. Now one of the major advantages that you get from an instrumentation amplifier is it has variable gain. Again, input impedance is quite high. It has high CMRR. CMRR means common mode rejection ratio. We already have seen differential gain. When you have 2 inputs, the differential gain we already have calculated in differential amplifier. Then there is another gain which is known as common mode gain. We call it ACM, common mode gain. Okay. So the ratio of differential gain and common mode gain is something which is known as CMRR. Usually we want very less common mode gain. That means if there is a common signal in both inverting and non-inverting terminal, we don't want that to get amplified in case of differential consideration. So usually we want the common mode gain to be 0, but in practice you will find there is some sort of common mode gain, and CMRR is an parameter which will help us to understand if the common mode gain is high or low. Okay. Usually it's we want a very low common mode gain usually. Then instrumentation amplifier also has low input offset drift. Now generally we use this instrumentation amplifier for small differential signal, for example thermocouple, strain gauge or current sensors, where the differential signal is very small. We can use this instrumentation amplifier, and it also provides a variable gain. So this is the basic structure of a instrumentation amplifier, which is consist of this particular amplifier consists of 3 different amplifiers: A1, A2, A3. Now if you look at this part of the circuit, it's nothing but a differential amplifier, and this part of the circuit is input buffer. So it's just a voltage follower circuit. In both the cases, it's just a voltage follower circuit, and this stage is known as input buffer. And then we have a differential amplifier part of this entire circuit. And if you change the resistance or resistor value of this particular resistor, if you change the resistance, you will get different gain. So that's why this is known as variable gain resistor. Now let us see or try to simplify the entire circuit. The idea is to figure out the relation between input and output. Then only we will be able to understand how this circuit operates. Again, in this case also, we will apply superposition theorem, because there are 2 different inputs. Let us consider one at a time. This will help us in simplifying most of the circuit consideration. So if we only consider say A1 and A2, A1 and A3, sorry, then you will find the output voltage is V1 out. So in this case, your output voltage is V1 out. That means you are only considering V1 input. And if you look at the V1 out, and if you consider the potential here and here as V3 and V4, then this particular amplifier structure will give you V1 out is equal to R4 by R3 into V4 minus V3. We already have seen the calculation in differential amplifier. So if you do the similar type of calculation, you will find your V1 out is R4 by R3 into V4 minus V3. Now A1 is a non-inverting amplifier because the input is connected to the non-inverting terminal of the amplifier. So you can consider your V3 is equal to V1 into 1 plus R2 divided by R1. So we also have calculated non-inverting amplifier output in our previous lecture. So your V3 is equal to V1 into 1 plus R2 by R1. Now in this case, your I is equal to V3 divided by R1 plus R2. So if you consider this potential, which is V3, and this potential, which is ground, and this current, which is I, then the same current will go through R2 and R1 because no current will enter inside the amplifier. So your total resistance in this case is R2 plus R1, and potential difference is V3 minus 0. So it's I is equal to V3 minus 0 divided by total resistance R1 plus R2. So your I is equal to V3 divided by R1 plus R2. Similarly, if you consider this potential as V4, your current I will be equal to minus V4 divided by R2 because this terminal is anyways ground, right? So this is again the value of I. Now if you put the value of I from this equation to that equation, you will figure out V4 is equal to minus R2 divided by R1 plus R2 into V3. Just do a little bit readjustment and you will figure out that the value of V4 is equal to minus R2 divided by R1 plus R2 into V3. So now you have the value of V1 out, you have the value of V3, you also have the value of V4. So let us summarize this over here. Your V1 out is equal to this, your V3 is equal to this, and your V4 is equal to this. Now, in this case, you can replace the value of V3 from this equation. Then you will get V4 is equal to minus R2 divided by R1 plus R2 into 1 plus R2 by R1 into V1. So here also you have the V3 value. Just put this V3 value in here, you will get the value of V4 is equal to this one. Now let us put the value of V4 and V3 in this equation, V1 out equation. So if you put those values V3 and V4 in here, you will end up getting this equation. Do some rearrangement and you will figure out that your V1 out is equal to minus R4 by R3 into 1 plus 2R2 divided by R1 into V1, right. So the output V1 out due to the input V1 ignoring V2 is equal to this one. This is the relation between your V1 out and V1 when V2 is absent. Similarly, in the next step, let us consider V2 only and ignore V1. So in this case, the amplifiers under consideration is A2 and A3. Now the output will be V2 out because the output is only due to V2 when we ignored V1. So V1 is not present in this circuit, and the potential here is considered as V6 and potential here is considered as V5. So your V2 out, again if you consider only this part of the circuit, is equal to R4 divided by R3 into V5 minus V6. So your V5 is equal to V2 into 1 plus R2 by R1 if you consider only this circuit, which is again non-inverting amplifier, and the calculation regarding the input and output we already have discussed. Just put that calculation over here, so you will get the value of V5 and V6, that is this one, is equal to R2 divided by R1 plus R2 into V5. So just do the same calculation that we have done in the previous case, consider the current, and then you will find the relation between V6 and V5 is V6 is equal to minus R2 divided by R1 plus R2 into V5. You have the value of V5, put the value over here, then you will get V6 is equal to this. Now if you put the value of V5 and V6 in V2 out equation, you will get the output is R4 divided by R3 into 1 plus 2R2 by R1 into V2. Hence your total V out will be V1 out plus V2 out as per superposition theorem. Now you have V1 out plus V2 out, and you put the value of V1 out and V2 out in this. This is your V2 out. We already have calculated the value of V1 out here. So you put both the values in this equation, you will get an expression similar to this. Now again, instrumentation amplifier is a differential amplifier where the gain depends on all these resistors. So one can change the amplification or gain just by changing the value of these resistors. It's nothing but a differential amplifier, and you can use the instrumentation amplifier again for those sensors where the differential potential is small in order to amplify those potential. Okay. Now this is the typical circuit arrangement of the instrumentation amplifier, where this R1 value is connected between the terminal 2 and terminal 3. That means in this circuit this resistor value or the value of this resistor is under your control. Rest of the things are inside the circuit or inside the IC. So you will get this resistance outside the circuit and you connect this resistance between second and third terminal of the IC. So just by changing the value of R1, you will be able to change the value of the entire gain, right? Then you connect V1 and V2 with terminal 1 and terminal 4. Then terminal 5 and terminal 8 is for supply voltage Vs plus and Vs minus. Your 7th terminal is the output terminal and 6th terminal is the reference. So you can connect an level shift resistor in or to shift the level. You can connect this terminal with say a voltage Vref, which will help you to shift the level, and you can vary this R1 in order to change the gain as it is shown over here. Now in this case your gain is V out divided by V2 minus V1, that is your input. So you connect your sensor between first and fourth terminal, and when there is a potential difference between these two terminals, that potential difference will get amplified and you can take this particular output from 7th terminal and put it in the next stage of your system, right? So in case your R3 is equal to R4 and R2 is equal to 9.9 kilo ohm, you will have a gain G is equal to 1 plus 19.8 kilo ohm divided by Rg. So this is the gain value if your R3 is equal to R4 and the value of R2 is 9.9 kilo ohm, right? So usually this is the case in case of an amplifier, because these three terminal R3, R4, R2, everything is inside the IC. So whatever value the manufacturer will put here, you have to take that value only. You have only control over the R1. So just by changing the Rg, you will be able to vary the gain. So this is the instrumentation amplifier circuit, and again this circuit is very important in sensor application. We have seen the amplifier AD8422 and the pin diagram associated with it, but as far as the amplifiers are concerned, there are a variety of amplifiers available in the market, and amplifiers are one of the major component of any sensor circuit or any sensor system, because amplifiers are also used to design filters. It also used to amplify the output that you receive from a sensor. In many cases you may find that the sensor output is of the order of say millivolt, and if it is in the range of millivolt, or sometimes it is say in the range of microvolt, in those cases just to operate the sensor, we need to amplify these voltages to say to a range of 1 to say 2 volts or so, depending on the system requirement, and for that purpose amplifiers are needed. Just like AD8422, one of the basic amplifier that you may find in system design is LM741. This is one of the basic amplifiers, but it's not only a few amplifiers that are available. You'll find a lot of amplifiers or lot of option, and all these amplifiers has their own sort of specification. For example, gain, the slew rate, and different other specification associated with amplifiers are different, and then based on that only you have to decide which amplifier to use. Now if you look at LM741 amplifier, this is also a kind of 8-pin amplifier where you have 8 different pins in 2 direction. This is how it looks, similar to an IC. You'll get an IC of this, And then you have offset different, like offset null. This probably is offset null. Then you have inverting input. Then you have non-inverting input. And then you have VCC here, which is the negative VCC. And after that you have positive VCC here. Once you have positive VCC, then the next one is the output, and this is again offset null, something like that. So this is how this is not connected. Okay, so this is how the entire LM741 works. It is also 8-pin device, and the numbering of the IC depends on uh, the inputs or the terminals that you have. For example, the first one is offset null. The second pin is the inverting input. We already have seen what is inverting input, what is non-inverting input, and then what are the circuits that actually you can make using an amplifier. Then the non-inverting input is the third terminal. Then you have negative VCC as a fourth terminal. Then again fifth terminal. So from here it should be like fifth terminal is offset null again. Then you have uh, sixth as output, seventh as VCC, and eighth again is a terminal which usually known as not connected terminal. But when you buy the IC, it will not be in this order. So when you buy it, the pins will be something like this. Say this is 2, this is 3, this is. So that is how these pins are arranged. And the symbolic representation of the same would be 1, 2, 3, 4, and then you have 5, 6, 7, 8. So you'll find there is a small symbol like this type of symbol in the IC that shows from where the counting will start, and then you go like this: 1, 2, 3, 4, 5, 6, 7, 8. So your 1 is offset null, then inverting, then non-inverting, then VCC negative, then the fifth one is again offset null, then the sixth one is output, seventh one is VCC positive, and the eighth one is like the not connected one. So that is the usual way of symbolic representation of this IC. So this is one of the basic amplifiers which you may use when you start working with amplifiers. And doesn't matter whether you have LM741 or this, in both the cases you will be able to design the circuits that we have discussed previously. You can design with both of them, but the choice of your amplifier would depend on the kind of gain that you want, what is the noise level that you want to achieve, or what is the noise level that you want to implement, what would be the range of your this system as far as the output of your sensor is concerned, whether the circuit should be low noise or not. Then you have low noise amplifiers available. What would be the drift, how much drift you want, and based on that you have lot of different options, and you can choose an amplifier accordingly. So usually mm, the job of an amplifier in most of the cases is like designing an active filter or amplification. uh, but again, as I have said, the amplifier will be decided based on the system requirement, as the different parameters that I've said. So you have to first check those parameters, and then you have to decide an amplifier suitable for your sensor system. And this is one of the major components when it comes to sensor system design. In the upcoming discussion, we will discuss about filters. So there are various types of filters. We'll start with active filter discussion, and during the discussion we will see the consideration associated with passive filters as well. Till then, thank you.